Oh, okay.
Yes, we can hear you.
That's great. I was a bit worried. Okay. Hello, everybody. So Lister is a heat flow probe, and so it's been selected to fly on one of the CLIPS missions in 2022. Then it's being built at the Honeybee Robotics. So as most of you know, so the Apollo 15 and Apollo 17 were able to measure heat flow successfully at their landing sites. Then, so the measurement for Apollo 15 was 21 million per square meters, and Apollo 17 had 16. So then, 20 years fast forward after the Lunar Prospector mission, so it turned out that the PKT has a higher concentration of heat-producing elements on the surface of regolith. So that's why it's been hypothesized that maybe the heat flow at Apollo 15 was higher because of this higher concentration of the heat-producing elements in PKT. So that's one of the hypotheses we have been wanting to test. Then also, so we can measure heat flow only at the surface of the moon, but so as most planetary differentiation models suggest, so the heat-producing elements are highly concentrated within the crust. So, so that's why of the heat flow we're measuring on the surface, we want to kind of differentiate, how much of the heat is coming from the mantle and how much of the heat is coming from the generated within the crust. So, so that's why by collecting more heat flow measurements, we may be able to answer those questions, particularly by testing those, answering those questions. For example, does the heat flow correlate with the surface abundance of heat-producing elements? Does heat flow correlate with crustal thickness? If the heat, substantial part of the heat is being produced within the crust, then if we have a thick crust, we have higher heat flow and vice versa. Then also, can we confirm that actually the PKT has higher heat flow overall and compared to other terrains and so forth. So, so that's why we propose to, we have been developing a heat flow probe that can fly on small lander missions so that we can deploy them in many different places. So, so the picture you see is the prototype we built last year. Then it's kind of sort of sitting sideways right now. So so here on the tip you see on the right is the needle probe. So that does all the measurements, and that's where the sensors are. Then so this kind of spools out to penetrate into the subsurface. Then the heat flow is obtained as the actually two separate measurements of a thermal gradient and a thermal conductivity. In order to acquire those measurements, so so the probe penetrates to about 3 meters into depth. Then at every half meter, we make measurements of a temperature and thermal conductivity. Then, oh yeah, by the way, so so this prototype weighs about 3.5 kilograms and is about the size of a shoebox. So it fits in a small lander, no problem. Then also, so this is developed specifically for CLIPS missions. So that's why it's designed to complete all the necessary measurements within one Earth day. Here you go. So this is the conceptual drawings for the deployment. So we're just using a sort of a drawing of a generic lander. Then because of this, the modular Lister is a modular instrument, and it's also very small mass. So that's why it can be accommodated in many different ways to landers. Then, so this example uses that the instrument is attached to one of the lander's legs. It could be also attached to like the underbelly of the lander if it needs to. Then, so then the penetrating cone and the needle that kind of spools out on what we call a boom. It's made of Kapton and glass fiber composite material, then it's still out just like a tape measure does on the picture on the right. Then, so in order to penetrate into lunar regolith, so the needle at the tip of the boom sort of penetrates and loosen the soil. Then also at the tip of the cone, we have gas jet coming up. So when the gas jet comes out in the vacuum, it expands rapidly. So the momentum of that force, using the moment of that force, we can blow out the loosened regolith out of the hole. So here, picture on the right is this is how we test this pneumatic drilling capability of Lister. So here we're using 3.5 meter tall vacuum chamber set up at the Honeybee Robotics. Then, so inside we have this PVC tube that is filled with regular simulant. Then the heat flow probe is set up at the top. Then we just test the closed sealed chamber and pump out, and then we test the pneumatic drilling. So the picture in the middle kind of took a snapshot of it, how the regular particle comes out of the vent. So this technique seems to be working very well. So in order to make necessary measurements, so at every half meter depth, when the needle sensor reaches the targeted depth, we stop blowing the gas. Then we push the needle into the soil at the bottom of the hole that is yet to be disturbed. Then first we spend an hour or so for the needle to thermally equilibrate with the surrounding soil. Then especially in the first measurements at the half meter depth, the instrument will be probably considerably warmer than the surrounding regolith because we deploy the probe during the day. So we just waited. We saw the picture, the graph here on the bottom shows you a sort of a simulation result. So that kind of tells you how the temperature of the needle is kind of cooling down in this 60 minutes of waiting period. Then, so it's not going to be completely equilibrate in 60 minutes, but because the thermal mass of the probe is small enough, so that's why if we just wait 60 minutes, it cools off enough so that we can extrapolate this trend cooling curve to estimate what the temperature of the regolith should be. So after this waiting period, so we this needle probe also has a heater. So then we turn on this heater. Then, as you can see, the temperature of the probe warms up accordingly. Then so we use how quickly we use the knowledge of how quickly the temperature of the probe warms up in determining the thermal conductivity of the regolith. So if for example, if the regolith is very insulating, then that means the heat that is generated at the needle will have a difficult time dissipating away from it. So that's why the temperature will rise relatively quickly. Then on the opposite scenario, if the regolith is more conductive, then it will allow the heat to dissipate away from the needle quickly. So that's why the temperature will not rise as high. So the graph on the left kind of shows you a compilation of the actual tests we performed in the vacuum chamber for the regolith of different conductivities. So the simulant of the conductivities, and then as you can see, for the lowest conductivity, the temperature rises the highest. Then if we just replot this graph for the heating part against the natural log of the time, then each actually measurement lines up along a straight line. Then the conductivity is obtained as is inversely proportional to the slope of this graph. So that's the technique. It's similar to the technique that was used for the in situ conductivity measurements for the Apollo experiment. Anyway, so just a summary. So the Lister is a compact modular heat flow instrument and can be accommodated onto landers of various configurations. And again, it will penetrate 2 to 3 meters into the lunar regolith and measure and temperature and thermal conductivity every half meter depth interval. So the heat flow is obtained as that's product of a thermal gradient and the thermal conductivity. And then it completes all the necessary measurements within 1 Earth day. Then it is destined to fly on one of the CLIPS missions scheduled for 2022. Thank you for listening.
Thank you very much. We have questions in the chat about the drill. So what might fall your drill first?
Sorry? Could you repeat the question?
What might fall your drill?
What? Sorry?
What might foil your drill?
What might? What might? Sorry, I can't understand the question.
What might stop your drill from working?
Yeah. Stop the drill.
So yeah, that's right. If we run into big rocks, yes, that could be a problem.
Okay, and all the testing you did were in simulated lunar regoliths with rocky inclusions, or yeah?
That's right. Yes, we started out with the pure JSC1A. Then we are now testing them with some nuggets of rocks in there to optimize our drilling performance.
Thank you.
Mm-hmm.